Welcome back to the next video, everybody. Today we're going to continue on with the proof of proposition 5. This is a hard one. Let's get into it. This is part 3. Let's recall a lemma. Let's let sigma be a finite set of primes in sigma rho bar, where rho bar is our plausibly modular representation. Define n sub sigma, as in video 11.11. Recall that rho bar is equivalent to rho sub frac m over t sub o mod frac m for some maximal ideal frac m of t sub o, and some gamma of level, let's say, n. Before proceeding, we're really going to need a twisted version of the following result from video 11.11, which we'll recall now. So we've already proven this. We called this proposition t sub frac m. It said there exists an isomorphism between t sub sigma, the type sigma Hecke algebra, and t sub frac m, and this is an isomorphism of O algebras that sends TP to TP for all primes P not dividing n sub sigma times L, where L is the characteristic of rho bar. Okay, so we already have this. We're going to need a different version of this. Recall from the previous video that we're now interested in finite sets sigma of primes P contained in sigma sub rho bar minus L, such that rho bar of Frobenius set P has eigenvalues alpha P and beta P in K. K is the field over which we're considering the representation rho bar. Satisfying alpha P divided by beta P is not equal to P plus or minus 1, or equivalently, the trace of rho bar of Frobenius set P squared is not equal to P plus 1 squared. And we called Q the set of primes little q in sigma, such that Q is 1 mod L. Okay, so we've kind of switched up which sets of primes that we're considering here. Just as in video 12.3, choosing an eigenvalue alpha Q of rho bar of Frobenius set Q for each Q in Q allows us to regard R sub Q, and hence T sub Q, via phi sub Q, as an O bracket delta sub Q algebra. Instead of working with gamma 0 n sub sigma as in proposition T sub frac m, the one that we just recalled, we're now going to work with a different group, gamma, which is gamma 0 n sub empty set intersect gamma 1 of m, where, as in video 12.6, this number m is the product of primes p in sigma minus q of those primes squared times the product of primes q just in q of those primes q. Okay, so we're going to change kind of which congruent subgroup we're working with. So let's continue. Let F be a new form in, I guess, like cal n sub empty set. This guy was defined back in a video 11.70. Unfortunately, you have to be kind of a master of definitions in this video. Okay. For each q in q, let alpha tilde sub q of f denote the root of x squared minus aq of f plus q equals 0 and k prime of f. So this is kind of like our local extension of q sub L generated by the Fourier coefficients of f, whose image in k sub f, the residue field, is alpha q. Similar to video 11.11, we'll let G denote the unique normalized new form in S2 gamma k prime f of trivial character, such that A sub p of G is A sub p of f if P isn't in sigma, A sub p of G is alpha tilde sub p of f and P is in Q, and A sub p of G is 0 else. Okay. Again, similar to video 11.11, the reduction G bar of G is the unique normalized eigenform in S2 gamma k prime of trivial character, such that AP of G bar is trace of rho bar restricted to inertia at P of Frobenius at P if P isn't in sigma. A sub P of G bar is alpha P if P is in Q, and A sub P of G bar equals 0 else. Again, really, like all of this, you should go back to video 11.11 to see similar arguments. Really, this means that G bar has coefficients in K and is independent of the choice of F in like fancy n sub empty set, just like how things worked back in video 11.11. Okay. This G corresponds to an ideal frac m in T sub O, and so we'll consider the maximal ideal frac m corresponding to this choice of G from here on out. Suppose that K contains the coefficients of all eigenforms of level dividing n sub sigma. Let fancy n prime denote the set of new forms G and fancy n sub gamma, which is the set of new forms in S2 gamma. You can see a video 11.10 for this definition, such that rho bar sub G is isomorphic to rho bar, and A sub p of G bar is alpha p for all p dividing n sub G over n sub empty set. Okay? Let G in fancy n prime be a new form with character psi sub G, and let Q sub G be the conductor of psi sub G. We know psi sub G has trivial reduction by construction, and hence L power order. We're now going to need the following result of Carriol and Livni. Proposition CL, let F be a new form of weight 2 and level n sub f, and let P be a prime such that P divides n sub f, the level of f. P isn't equal to 1 mod L, and rho bar sub f, the L-adic representation, is unramified at P. Then the trace of rho sub f of Frobenius at P squared is P plus 1 squared in K sub f. Here's some references for you for a proof of this. We're not going to go through a proof of this. I haven't been through it actually. It's a good place to start would be Diamond-Taylor's non-optimal levels of mod-L modular representations for some kind of background information. And then you can go into the hardcore Carriel references and stuff. Okay, so let's continue. By proposition CL, if P is in sigma and not in Q, then rho sub G is unramified at P, and hence N sub G cannot be divisible by P. By basic but deep properties involving Carriel's hard theorem of rho sub F, you can see, for example, theorem 3.1e in the DDT notes. We've covered those properties before, though, in this playlist. And also the fact that trace of rho bar Frobenius set P squared isn't P plus 1 squared, we must have that N sub G is N sub empty set times Q sub G. We'll let C sub G denote the character of Z mod Q sub G Z cross of L power order, such that C to the negative second sub G is the primitive character associated to psi sub G. This is kind of similar to some things we did earlier in this chapter. Then G tensor product C sub G is the sum of the C sub G of n's times A sub n of G Q to the n, which is in fancy n sub Q sub G, which is in fancy n sub Q. Okay, so continuing, we need a new lemma. Lemma fancy n prime. It very simply says that the map that sends G to G tensor C sub G is a bijection between fancy n prime and fancy n sub Q. The proof is very straightforward, actually, and this video is going to be quite long, so in an effort to keep this video appropriate length, and because we're simply really just proving a variation on an already known result, we'll refer to the reader to lemma 4.9 in DDT. The proof is straightforward. I'll type this up in the notes when I post public notes for Fermat's last theorem for this chapter. Okay, so these guys are in bijection. Let's continue. Let's recall that T sub O contains the diamond operators bracket D for D and Z mod M Z cross. And note that bracket D minus 1 is in frac M for all D, because frac D maps to character values of F, but F has trivial character. That's the point. So let H prime denote the kernel of Z mod M Z cross, which surjects onto Z mod product over Q and Q of Z cross, of course. And this surjects onto delta sub Q by definition. So we'll let H denote the kernel of this composition. Okay, or H prime rather, excuse me. Since the order of H prime is not divisible by L, we know that the sum over D and H prime of bracket D cannot be in frac M, which means that if D is in H prime, then bracket D is 1 in T sub frac M. This means that T sub frac N can actually be regarded as an O bracket delta Q algebra via what map? Just send D to bracket D. Okay. Now recall that T sub Q is also an O bracket delta sub Q algebra via the map from O bracket delta Q to RQ to TQ. So this was like a huge result that we had before. If P is a prime not in Q, let X sub P denote the unique element of delta sub Q such that X sub P to the negative second is P bar, that's what we're going to denote the image of P in delta Q by. Kind of like a little note here. Since delta Q is an L group, the map X to X squared is an isomorphism, so this actually makes sense. Okay, now we're going to state and prove our variant of proposition T sub frac M that we've been aiming at for this whole video. We'll call it proposition T sub frac M twist. And it says, let sigma and Q be a finite set of primes as in slide 3 of this video. Then there's an isomorphism between T sub Q and T sub frac M of O bracket delta Q algebras, such that T sub P is sent to XPTP for all primes P naught and sigma, with P naught dividing L times the conductor of rho bar. Okay, so let's prove this. So in large K, the field that we've been working over, so that we are in the setting of lemma fancy N prime, we're going to define an isomorphism of K algebras kappa from T sub frac N tensored up to K, to the product of like one, copy of K per new form G in fancy N prime. And this isomorphism is going to have the following properties. Kappa of T sub P sub G, so the Gth factor, is A sub P of G, if P isn't in sigma, or if P divides Q sub G. Kappa of T sub P sub G is going to be 0 if P is in sigma but not in Q. Kappa of T sub P sub G is going to be the root of X squared minus A sub P of GX plus psi sub G P times P with reduction alpha P if P is in Q but P doesn't divide Q sub G. And finally, kappa of D sub G is going to be psi sub G of D for all D in delta sub Q. Okay, so recall from lemma T sub K in video 11.10 that we already have the following isomorphism from T sub frac N tensor K to the product over new forms G and fancy N sub gamma of the product of elements frac P and like fancy M sub G of A sub KG mod I sub KG sub frac P. Let's remember some notation here. This fancy M sub G is the set of prime ideals in A sub KG mod I sub KG, whose preimage in T sub O is contained in frac M. So this was like a certain, I mean, you're going to have to go back to that video to get all of this notation because I can't review it here. Okay. But like we have all this notation already. I just told you what this is and what these are. This was like a certain guy contained here. We quotient out. Okay. Okay, if G is not in fancy n prime, then M sub G is empty. If G is in fancy n prime, then fancy M sub G consists of the prime ideal corresponding to the eigenform whose eigenvalues we just prescribed. And you can easily check that in this case, the factor A sub kg mod I sub kg frac p is just k as desired. Okay. Next, if we view T sub q as a subalgebra of the product of f in fancy n sub q of k, so kind of one factor of k per f, and match indices via our bijection that send, okay, so like we have this bijection from before in this video that sends G to G tensored up to C sub G. We're going to call this tensor product here just F, okay? And so this is kind of the new notation for that bijection. So if you view T sub Q as a subalgebra of this product here via that bijection, you get an injective homomorphism of O bracket delta Q algebras, which we'll call kappa prime, from T sub Q to the product over G in fancy n prime of K. And this injective homomorphism satisfies kappa prime of T sub P is C sub G of P times A sub P of G sub G, which is kappa of X P TP for primes P naught and sigma such that P doesn't divide L times N sub empty set. But see, T sub Q is generated over O by exactly these kinds of T sub P's. And so kappa prime of T sub Q is contained in kappa of T sub frac M. On the other hand, the image of kappa prime certainly contains the image of delta Q under kappa, hence contains kappa of, for example, bracket D for all D and Z mod MZ cross, and kappa of TP for all P and sigma with P naught dividing N sub empty set times L. Okay. And so really, we just have to show now that kappa of TP is in the image of kappa prime of TQ for P dividing N empty set L times the product of Q for all Q and big Q. Okay, so to do this, consider the following composition. So we'll take phi Q from RQ to TQ, and then we'll take the kappa prime we just built from TQ to the product over the G and fancy n primes of K. The push forward of the universal type Q deformation rho UQ is equivalent to the product of rho sub G tensored up to C sub G, which means that the product of the rho sub G's is equivalent to the push forward of rho sub UQ tensor C to the negative first sub Q, where C sub Q was defined in video 12.3, so another definition reference. I'm sorry about that. If P is a prime dividing M sub empty set, then kappa of TP is the image of Frobenius at P on the IP coinvariance, so that kappa of TP is in kappa prime T sub Q. If Q is in Q and G is in fancy n prime, then the push forward of C to the negative first when restricted to G sub Q times C sub QQ. This was another definition from video 12.3, if you recall. Push forward to where? To the G component. This is an unramified summand of rho sub G restricted to G sub Q, whose reduction sends Frobenius at Q to alpha sub Q, essentially by construction. Hence, this character maps Frobenius at Q to kappa of T sub Q, and so kappa of T sub Q is in kappa prime T sub Q. Finally, if L doesn't divide M sub empty set, lemma T sub R from video 11.10 shows us that kappa of T sub L is also in kappa prime T sub Q, and so all of the kappa T, of the Hecke operators are in kappa prime of T sub Q, which is what we wanted. And there we go. We finished the proof of the twisted version of proposition T sub frac M. That was probably the single hardest part of this chapter. I think I have one more video on 12.5, and then that will finish the proof of proposition. Let's see, what are we on? Proposition, I forget, is it 5 or 3? Proposition 5. And then I think after the next video, we'll be done with proposition 5, and then we'll be able to finally prove R equals T in the minimal case. That will finish the proof of R equals T in totality, which I think will finish the proof of Fermat's last theorem actually completely, minus some facts that were missing on the flat deformation functor, which will get its own chapter. And so thank you for watching, and I'll see you next video.